One select.
I never responded, like, over the monthly break when I sent her an email about the,
Did you guys want to break them?
project.
Okay, so let's, ooh, it's bright.
No, we're still.
Wait, 30.
All right, so let's look at a couple here. There's a couple things that I think would be useful to see.
What's going on? That's what I'm gonna do, like, one is, hell.
The first part is, the mechanics part is pretty similar. Pretty similar. Lots of, I mean, hard problems where you have to do free body diagrams, consolidate forces, kinematics, would be involved.
We're learning 3.7, right?
No, 3.6. 3.6. I'm gonna give you a little 3.6 assignment. Yeah, and we're gonna get right to that, but this is, I want you to get some additional practice on a couple of these things. So let's look at a few of these. Let's look at something like this guy. Here's a good one. So,
That's so cute, Jimmy, right?
hi,
You're back. Just there.
Michelle's abusing me.
So,
Okay.
Maybe it's-
Let's just find everything for this function, right? So we want relative extrema, we want inflection points, et cetera, et cetera, et cetera.
all the fire.
And so let's.
No,
you're
You know what?
messing me
It's
up.
kind of been
Put
a
that away.
long weekend.
So let's go through. We're going to come up with a table, right? And the table is huge. If you can get to where you can populate that table and really are good with the table, you're going to get a ton of mileage out of that in the future. So first thing we want to do is let's find the domain, and don't skip this step. This is important. We need to know what the domain is so we can know where to look for critical numbers and where critical numbers don't matter, right?
Would it be anything less than 0?
No, wouldn't it be
Okay.
anything that makes
Greater.
it negative?
Yeah.
Say it again.
anything less than-
Anything that makes it negative.
Anything that makes it negative,
Anything
good.
less than 4.
Okay, less than 4. And here's kind of a maybe a tactical approach to finding the domain. So what I always like to talk about for this is, where is the red flag? We only have two things we look for, right? Or we have dividing by 0, not an issue, or even roots of negative numbers. Well, that's an even root, right? So then whatever the argument of the even root is, what we really need to just have is whatever's inside that square root has to be non-negative, right? So then here's how we can show this. We could just say the bubble has to be greater than or equal to 0, right? And what's in the bubble? Yeah, 4 minus x. And so now we can solve that for x pretty easily, right? How would I solve that inequality for x? Yeah, I would add x to both sides. If we subtract 4 and divide by -1, we got to remember to flip the sign. It's way more steps. It's always easier, in my opinion, to just push variables, or push terms left or right than it is to have to isolate them when you have to divide the things, right? Does that make sense? So we'll push it to this side, and then we'll just flip the inequality around. And so our domain then, would you agree, is just x is going to be less than or equal to 4? Okay. We good? Okay, so there's our domain. Good. So now we got to do some calculus, right? And we could even start on the table. Yeah, we could start on the table, I guess. Why don't we? So we'll scoot way down here.
So we're gonna have like both y prime and y double prime.
We're going to have, right, y and y prime and y double prime on this one. I'm just going to deal with the first row of the table for now, though, because that's where the domain is. So we're just going to go values less than 4, so this will be our 4. What kind of bracket am I going to put up there? Yeah.
One of those.
Yeah,
Yeah.
Not a print.
What kind of bracket?
Yeah, I guess bracket, yeah.
Wait.
Okay, so there's our domain, right? Okay. And now we get to do calculus. Okay, but to do calculus, we want to rewrite that function how?
Into 4 minus x to the
Okay, 4 minus x to the 1/2. So we end up with y equals x times the quantity 4 minus x to the 1/2. All right, so now we got to do some differentiation, right? Okay, so talk to me about the derivative. What's going to be at the outermost level? What kind of rule is going to dictate this derivative? Product. Right, I got a product of two things, right? So then y prime is going to equal what? X times right, negative 1/2. Everybody see why? Okay, times negative 1. And let's just put the negative 1 about with the 1/2. Okay, make sense? Okay, plus what?
1 times 4 minus x.
Okay, so 4 minus x to the 1/2 times the derivative of x, which is 1. Good. All right, so what can we do here then? So this is the part where we want to do some factoring. Okay, what can we factor out? We look for like bases. Okay, so yeah, here are like bases, aren't they? Right? All right, so I've got these like bases. Let's factor out front the least common power of our bases. In other words, the wimpiest power of our bases is all we can take out. So what's the smaller of the two? The negative. Good. So we can extract. We can factor out a 4 minus x to the negative 1/2. There's one other thing that I like to do here also. If I have any fractions, let's factor out the least common denominator, right? So the greatest common multiple of all the fractions. Well, there's only one fraction and it's a 2, right? So let's go ahead and pull out front a 1/2. Okay, dividing by 1/2 is equivalent to multiplying by 2, right? You see that that's exactly equivalent to distributing through a 2, okay? So then what are we going to be left with inside? So from our first term, what do we get? Well, this goes away, right? And that goes away. So what am I left with? Negative x. Everybody agree? In the first term? Okay, I'm going to circle this plus sign so we can keep track of it. Right, that's the plus sign that's separating the two terms, right? So what about over here? Factoring out a 1/2 gives me a coefficient of 2. And then what about this? This is the part I want you to get a handle on here, because this is the part that's going to look a little weird. So I wanted to do some problems specifically like this so you can get used to it. If I'm factoring out this base, hand to the minus 1/2, and I started off with hand to the 1/2, what am I left with? No. Hand to the what? No. To the 1. There's why. What I'm left with is when I factor out front, factoring out is dividing away, right? So what I'm left with, what goes here is going to be what I started with divided by what I factored out.
Oh, it's instead of negative?
Aha, does that make sense?
Minus 1 is.
Good, okay, so, right, does that make sense? When I factor out, I'm just dividing it away from each term. Does that make sense when I say that? Yeah. Okay, so then I'm left with the base 4 minus x to the 1. Okay, that shouldn't be surprising. Shouldn't be surprising because I've really got a 4 minus x to the 0 here in the first term, correct? Because it was completely, I factored it completely away, right? By the product rule, this base of 4 minus x appears once by itself, like the way it started, and it's going to appear once to a power that's 1 less than that because of the power rule. Does that make sense? So it makes sense then, in hindsight, after we factor out the fractional part, that what I'm gonna be left with is that factor, that base being to the 0 power, so non-existent in one term, and 1 power higher, which is to the first power in the second term. It will always work that way. Okay? Is that, we'll do another one, so you get a little more practice with this, but you see what I'm getting at there?
Say that again.
So you're always gonna end up with, when I have a like base to fractional exponents here, right? We've done the product rule. So by virtue of the product rule, these exponents are always gonna differ by 1, right? And so when I factor that out, the fractional exponent is gonna end up as part of the greatest common factor, but what remains will always show up in one of the two terms to the first power, because it's gonna be completely factored away from one term, and in the other term, it's gotta be a 1 because the powers must differ by 1 by virtue of the power rule.
Makes sense.
Okay, right? And so just kind of seeing those are the kinds of things that make you, I think, a really good mathematician. If you just kind of start to see those little, right?
Sure.
And they start to become intuitive, and then math gets easier. So then all we have to do is just clean this up, right? So then we end up with what? So on the bottom, we've got a 2, and we've got a square root of this, right? And then on top, we've got, looks like 8 minus x minus 2x, so something like that. Everybody agree? Okay, questions? Okay, so now let's go next step. We'll come back and get our critical numbers later. So then we've got a quotient rule here, don't we? So what's the quotient rule gonna give us? And we'll go ahead, we could pull that 1/2 out front, but we'll just absorb it into the bottom. No big deal. Sometimes I do that. It's just less to remember to distribute later. It's just one little thing. So quotient rule tells us
ID high,
low-D high minus high-D low, right?
Please.
So we get 2 times, I'm gonna write these as fractional exponents, 4 minus x to the 1/2, right? Times the derivative of the top, which is what? Good, -3. Minus, right, it's quotient rule, minus high D low. So the top is 8 minus 3x. Now what about the derivative of the bottom? What's that gonna give us?
Wouldn't it be 1 parentheses 4 minus x?
Yeah, we got this 2 out in front, and that's a 1/2 power, isn't it? Right, so when I multiply the 1/2 times the 2, conveniently they cancel. And then I just get 4 minus x to the negative 1/2 times -1, but where could I reflect that -1?
Just in those, you can change the addition.
Yeah. Okay, everybody see that? Okay, all divided by bottom squared, which is what?
4
Times,
minus x.
okay? Everybody agree? Okay, good with that? Okay, so now comes the cleanup process, right? So once again, we want to extract as much as we can. So we've got, looks like only one like base on the top, same as before. Right, so we could factor out on the top a 4 minus x to the -1/2 again. Times what's going to be left over then?
Wouldn't you have to multiply the first thing by 2? Or the,
Well, okay, but I didn't take out any fractions this time. Right,
Oh.
see the difference? Okay, so I'm just left with, and then what do we end up with? So this is gonna be gone from that term, right? And what about the first term? I'm gonna have 4 minus x to the 1/2 divided by 4 minus x to the minus 1/2, so what's gonna happen? 4 minus x to the 1, good. Okay, so there's our 4 minus x to the 1 times 2, so I'll put that 2 out front, how about?
Can we just make it a -6? Or can we just do the whole?
Oh, yeah, there's that, yeah, right, sorry, there's that negative, so right, it should be a
Would
negative.
we wanna just do it in all one foul swoop? Just
Yep,
make it
you would.
-24?
How are you gonna do that?
you multiply.
Because you'd have to distribute through the whole thing.
Yeah, I know.
Yeah.
Well, yeah, -24 plus the 6x.
So, I mean, I suppose you could, I'm gonna do it, I'm gonna go like this,
I'll do it that way, but.
and then over here, what are we left with?
8 minus 3.
8 minus 3x. And because we're adding, we don't need parentheses, right? All divided by 4 times the quantity 4 minus x. Okay, so then we can combine, look at this stuff right here. Exactly, what's that all gonna become?
The 1/2. Wait.
So here's a rule, and it's ironic that this is what I'm talking to my honors algebra 2 class about right now, but there's a better version of the quotient of powers. Let me just quickly, I'll show you this to you. It's not like it's a high power thing at all. So if we've got, excuse me, if I've got some base, let's say we've got a to the m divided by a to the n. You're always taught that that's equal to a to the m minus n, which is true. It's also equal to 1 over a to the n minus m. Why would we write it that way? The reason we write it that way is if the bottom, we always want to write powers in terms of positive exponents. Or, I mean, not always, but typically we do when we simplify something, right? And so what if we've got like bases, but the bottom power is bigger than the top, the bottom exponent? Then the rule is really simple. The rule, as I teach my Algebra 2 students, is just keep the base where it has the most power and subtract the other exponent, right? So using that thinking on this problem, we've got like bases of 4 minus x. 1 is bigger than -1/2. So we'll keep the base on the bottom to the 1 minus -1/2, which is what? 3/2. See what I'm saying? So then on the bottom, we'll end up with 4 times the quantity 4 minus x to the 3/2. And on the top, we just get what we get. So we're going to have here 6x plus -3x is, looks like 3x. -24 plus 8 is -16. Everybody with me? Okay. So now we can fill in our table, can't we? So let's look at our first derivative function. Okay, where are our critical numbers going to be? Okay, where the bottom is 0. Where does the bottom equal 0? At 4. Okay, 4 is our endpoint, right? Okay, so it can't really be a relative extremum. If we're looking for, what are we looking for here? If we're looking for, on this problem, relative extrema, points of inflection, and asymptotes, okay? I mean, I can put it on there, it's not going to hurt anything, but does it have any potential as a relative extremum? I mean, some books would say you can have a relative extremum as an endpoint. I would say you can't. But, you know, so we can either use it or not. Doesn't matter. Okay. It's a place where this derivative is undefined. Any other critical numbers? Yeah, top equals 0. Good. The numerator, so the y prime equals 0 when the numerator is 0. And when's that going to be? At 8/3. Good. Okay, so then, yes, when we start adding our other rows, we do get a 0 at 8/3. Okay, so we'll put it right there. So that's going to be a 0 of the first derivative, right? Okay. 4, if we want to do this, it's undefined. Oops, sorry, not there. Well, actually, no, it's not. Never mind, right there. So what about the second derivative? So what are we getting there? 16/3, okay. So 16/3 is gonna be like right here, right? It's, well, actually, hang on, 16/3. That's bigger than 4, isn't it? Right, so is that a critical number? No, it is not. And where does the bottom equal 0? At 4. So once again, this is kind of superfluous, but we could put an undefined there if we want, right? So we want to analyze this thing. What can we do? Second derivative test, right? What's the second the sign of the second derivative at 8/3? Well, let's just check the values of the numerator and the denominator. At 8/3, 3 times 8/3 is 24/3.
It's 8.
Oh, whoops, it's 8. Yeah, 24/3 is 8. Whoops, yeah. 8 minus 16 is negative. Bottom is 8/3 is going to be positive, right? It's in our domain. And so what's our overall sign?
Positive.
Negative. And so we got a 0 first derivative. That's a horizontal tangent. And we've got concave down. So that is a what? Relative max. Okay. And so then probably the only other thing to do here would just be to take our limits at the endpoints, right? See what's going on. So the function is defined at x equals 4, and what's the answer?
4. No. 0.
0. Okay, so we could do this, right? We could fill in that endpoint. Okay, we could plug in 8/3 also. What are we going to get for 8/3? Oh, yikes. 4 minus 8/3, that's 12/3 minus 8/3 is 4/3. So we're just going to get some 8/3 times the square root of 4/3. So that's going to be 16 over 3 to the 3/2. Or 16. Yeah, that's
I think that.
16 over 3 to the 3/2, I think is what it is.
Right.
Yeah. And we could turn that into a, I mean, you get the idea. Okay, so those are the coordinates, if we wanted them, for our relative max. Now, what about the limit at the left side? Okay, let's go back to our function and let's ask, what's going to happen as x approaches negative infinity? What's going to go on? As x approaches negative infinity,
It's gonna negative.
we're going to get a negative, we're going to get infinite for sure, right? And we're going to get negative times positive, right? And so the limit then is negative infinity, right? And that's everything we need, isn't it, to do our graph? Sketch a graph of this thing.
Is that, we're using 3/2 on the 8/3?
Yeah, that's supposed to be a 3 to 3.
Okay.
And it's probably not even important. We just want to get a sketch in it. It's just some relatively small positive number. So we end up then with, if we want to sketch this thing, so let's just say that's, the zeros there, right? So what do we get? we get an endpoint here at 0, right? We get a relative max at 8/3, so that's what, 2 2/3, so something like right here-ish, right? And then might as well get our intercept. What do we get at 0? What's the function's value when x is 0? 0, okay? That's a root, so that's helpful. And so if I sketch this thing, doesn't it just kind of do something like that? Because the concavity never changes, right? It's always concave down. Make sense? Okay.
So would you put an arrow on the side that's going towards?
Yeah, it's just going,
But
right.
not on the floor because of.
No, not there, that's a closed endpoint.
Right.
Yep.
It's like almost like a hybrid sentence.
Yep. You're right. Okay? So there's a lot of moving parts in that thing, but you get the idea? That's a good, trust me, that's a good representative problem. Those are the ones that,
Have a good day.
how much time we got?
Like,
2 minutes.
Oh, so we have a little more than that.
5 minutes. What's the assignment supposed to be?
I'll put it up. It's gonna be, I'm not gonna give you a ton, but I want you to do a few problems where the goal here is, so this is tables, right? What I wanna see on these is, and I'll have you maybe, I don't know, somehow maybe all of you turn these in or something, but what I wanna see from you is I wanna see you build a table and then do a little sketch for each one of these. I won't give you a ton of them, but go through the whole process. Incorporate all the parts of those cool tables.
Have you seen La La Land, Mr. Oyer?
I have not.
It's a good movie.
Is it?
It's one of the best movies I've ever seen. I hate musicals.
Okay, I got kind of a cool one for you. Let's do, we don't have much time, but let's just talk about this one. This is kind of a fun problem. So, here's the shape of the curve. F of x has this form. Ax cubed plus bx squared plus cx plus d. And here's the graph. Here's a sketch. I don't even need the axes in there. I'll just get rid of those.
So I'm guessing this is all in the first and fourth quadrants, or-
It doesn't even really matter. What in the world could we do?
Concave up, concave down, and intercept.
So we got concave up, concave down,
Inflection
point of inflection. Okay, are there any extrema? Okay, so if we wanted to come up with, and all we're trying to do here is come up with conditions for the coefficients. Can we constrain the, we can't pin down, there are no points on this graph, right? So we can't determine what A, B, C, and D are. There's gonna be an infinite number of possible answers, but there may be some conditions on those. This is a pretty cool problem. So what would happen if we were to like take derivatives? What's the first derivative gonna be?
3ax squared plus 2bx or 1bx.
Plus C?
I think 2
Okay.
is pretty.
So what's one condition you could impose based on the fact that there are no relative extrema?
That is accurate. Well,
Doesn't equal 0.
Okay, that it never equals 0. Yeah, right? That it never equals 0. So if we set this equal to 0, then that means there should be no solutions, right? Everybody agree? So what's one way that we could say there are no solutions?
x does not equal 0.
It has to do with the good old quadratic formula. This is pretty cool. Remember the guy, you probably Algebra 2, Honors Algebra 2, talking about, hopefully about the discriminant? Value of discriminant.
That word.
Okay, this is, I'm glad we're doing this thing, because this is pretty big. This part right here, under the radical, is the discriminant. Think it's the discriminant because it discriminates between the kinds of answers you'd expect. think what would happen. It's the only red flag in the quadratic formula, right? Because obviously a is not equal to 0 or it's not a quadratic function, right? So this is the only red flag. If the argument of the radical, call it the discriminant, is negative, are you going to get any real answers? No. You're going to get complex solutions with imaginary parts. You need eyes in them, right? If it's positive, what's going to happen? Then you're going to get real answers, and how many are you going to get? Two. One for the plus and one for the minus. If it's 0 valued, then essentially it has no impact on the answer, and the plus and the minus degrade to a single answer, right? And so the discriminant then tells you that at 0 value, you expect one double root, so one real solution. If it's positive, you're going to get 2 real solutions. Negative, you get none. So what value should it have here? What sign should it have?
Positive.
No.
None.
None,
No sign.
right? It should be negative because there's no place where this function would ever be equal to 0 because that would be a critical number. See what I'm saying? Right? Well, to be continued.